the relationship between position and velocity graphs. Let's take a look. We have a kitten right here at, let's count, 1, 2, 3, 4, 5 meters. Okay, kitten, please do something. Please move. Please. Something, do something, move, left, right. Okay, I guess cats do their own thing and the kitten just wants to sleep. That's fine, we can use that example. So, the kitten is at 5 meters, is not moving. So if we start the clock, look at the graphs. The position is remaining constant because the kitten is staying still. It's staying at 5 meters and is going nowhere. And take a look at the velocity graph. The velocity graph, since the kitten is not moving, the velocity is exactly 0 meters per second. The speed is also 0 meters per second. So the line is right on the axis. Now we can write the equations of the graph. The kitten starts at 5 meters, and every second the cat is moving 0 meters forward, aka not moving at all. So you practically don't really even need this. It's still good to show, but you could just write x equals 5 meters, and that would be the equation of the line. Now for the velocity graph, the velocity is exactly 0 because the cat is not moving. So it's just v equals 0 meters per second, and that's it. So since I need something more exciting than a stationary graph, we have to switch from a kitten to a puppy. So this puppy will be a little bit more energetic. So, puppy, do something. So look at this. The puppy is moving in the forward x direction. And remember, the origin is important. It is a good habit to always draw a number line for a lot of the problems because it really helps illustrate what's happening. Because, physics is more than just algebraic equations. It represents something happening in reality. So to do that again, the puppy starts at 1, 2, 3, 4, 5 meters. And look at the position graph. It's increasing. But the velocity graph is just a flat line because the puppy is moving at a constant velocity. It's neither slowing down or speeding up. It's just moving at some constant velocity. So the line is above the axis. So let's say the puppy starts at 5 meters, well, which is true. And, this number, it's not too important. It's just illustrate the point. Let's say every second, the puppy moves 2 meters forward in the x direction. So right here, this number would be 2 meters per second, and it's a flat line above the axis, so the velocity is exactly 2 meters per second. Now, what we can do is this. Take a look what we're doing here. We are shifting. We just shifted the origin right here. So the puppy is going to do the same physical thing, but take a look what happened by changing the placement. Is placement a word? By changing where we put the origin, it changes the initial position of the puppy. So let's say the puppy starts in the same physical location, but by redefining where the origin is, we redefine the initial position. So instead of saying starting at 5 meters, let's say the new initial position is -3 meters. The puppy is still moving forward at 2 meters per second, i.e. every second the puppy is moving 2 meters forward. So you can see by shifting the origin, it did not affect the velocity graph, but it affected the position graph by shifting the entire line down. It just basically changed, the y-intercept. The slope is the same, etc. So if we kind of animate this again, so the puppy starts at the same physical location, but we redefine the origin. So imagine, having a race and you're basically repainting the starting line somewhere else. So look at this. So the puppy's going to do the same motion as before. So you can see it's exactly the same. As you can see, the graph shade in blue. Okay. Let's reset the clock. Let's reset the clock. We'll erase the graphs. So let's say this is time 0. And instead of the puppy moving forward, let's say the puppy is moving backwards. So puppy is moving backwards like this. So you can see the slope is now negative. It is a negative slope on the position graph because your velocity is now negative. So the puppy now, it started at 6 meters, and every second it's moving negative 2 meters in the x direction. So it's now moving in the negative x direction according to our origin. And take a look. The velocity graph, this line right here is below the axis. So this is a constant negative velocity of 2 meters per second. Well, negative 2 meters per second. So negative 2 meters per second. So negative slope, negative velocity. So for the time being, your options for velocity graphs are above the axis, on the axis, or below the axis. And they're going to be really above or really below depending how big the number is. Now let's use a position graph to calculate average speed and velocity. So we have a compound graph here. So say the dog starts at 2 meters and goes to 6 meters, and then goes back to 4 meters. So take a look at the velocity graph. You're moving in the constant positive velocity in the positive x direction. Then the dog starts moving in the negative x direction. So let's look at line segment 1. Delta x, you're going from 2 to 6. Delta x is, well, 4. It takes 2 seconds to go from 2 to 6 seconds, 2 to 6 meters. So 4 divided by 2, the average velocity for that line is 2 meters per second. You can clearly see that this line segment here is a negative slope. So the first line segment, you're going forward 4 meters. So 2 to 6, 4 meters. 2 times 2 is 4. Now line segment 2, you're going from 6 to 4. You're changing your position by negative 2. Be careful with the negative signs, right? Because remember, it's always the final minus the initial, so it's really 4 minus 6. So 4 minus 6 is negative 2, and that takes 2 seconds. So the velocity is negative 2 divided by 2, negative 1 meters per second. So the important thing I want you to realize is the position graph and the velocity graph correspond perfectly. So you can see this graph went from 2 to 6 meters. So this area is 4 meters because the average velocity was 2. You went 2 meters per second for 2 seconds. This total area, which is displacement, is 4 meters. So 2 to 6 is 4 meters. The second graph, misclicked right there. Let's do that again. Okay, 1 second, just getting that. Okay, got it back. So, kind of broke my train of thought right there by misclicking, but line segment 2, you're moving at negative 1 meters per second for 2 seconds. So you're going negative 2 meters. And you can see it. So the big thing here is you can see that there's a correspondence between the position and the velocity graph. Because everything has meaning in these graphs. You know, this y-intercept is the initial position at time 0. The slopes, these slopes right here represent velocities. And for a velocity graph, these areas represent displacements. One final thing. Wait, are you done yet? No, we're almost done. We're almost done, okay? Just another minute. So let's calculate the average speed and average velocity. Average speed is the total distance divided by the total time. So take a look at the graph. You start at 2, you go to 6, so that's 4. Then you go from 6 back to 4. So 4 plus 2 is 6. And you can see from this graph, 4 plus 2 is 6. So the average speed is 6 divided by 4, 1.5 meters per second. Now, the average velocity doesn't care about, let's say this graph went up and down, up and down, up and down, up and down. It doesn't really care that you went to a million different places. It only cares about the starting point and the ending point. The starting point starts at 2, it ends at 4. So your change in position is just, well, 2, and the total time is 4. So the average velocity from 0 to 4 seconds is simply 2 divided by 4, or 0.5 meters per second. You can also get the delta x by saying 4 minus 2 is, well, 2. So a little bit about position and velocity graphs. They're all related. The big thing is to realize it's why it's so important to draw the axes, to always include the units, because they tell you physical meaning. So if you neglect to draw your axes and write your units, it gets very confusing very fast. So that's that. This should help you on the current assignments. So until the next video.